Good morning, ladies and gentlemen. Let's talk about capacitors again. Okay, so a capacitor, if you guys remember, this was the capacitor right here. Okay, and it has two metal plates with opposite charges on each side. Now, how the heck does it get those opposite charges? Well, it starts off.
You might as well just start over with two black lines.
Yeah,
those
I know.
area...
Like, let's see. They become charged. Let's see how. Okay. So we've got our two metal plates. La-di-da-di-da. Okay, negative, positive. Okay, and so what happens is we pump electrons. We have some sort of generator pump that pumps electrons from onto the plate, right?
Well, if it takes an electron off of the top plate, what happens to the top plate?
So yeah. So we take an electron off of the top plate, and the electron moves down here.
And you put it on the bottom plate.
Okay.
That makes the bottom plate negative.
Which means the top plate becomes...
Because it's missing an electron.
Yeah.
And the bottom it has one. So if you
Okay.
take another electron off.
We move it down here. Okay. And then this one now has a 1+ charge.
Yeah.
We take another electron.
So for every electron you take off the top makes it more positive, and every electron you put on the bottom makes it more negative.
Yeah.
Well, what kind of forces are going to be going on here?
Okay, so we have attractive and repulsive forces in here.
Yeah, well...
And if I was to throw a 1 coulomb charge in here, oh, sorry, this is my 1 coulomb charge. A 1 coulomb charge in here, what would it do?
It'd be repelled from the positive and attracted to the negative.
Right, okay, and so then what we have is, let me go to my next slide up here actually.
Well, actually, let's play with this.
Oh, yeah. Okay, so, let me go ahead and twist this guy up, okay.
So she's doing work
Oh yeah, I'm doing work here.
on this.
I'm doing work on this, okay. Ooh, look at that.
Try that again. Okay, she's doing work on the Wimshurst machine. It's pumping electrons from one side to the other. If I do this,
Woo!
you see the spark?
Yeah, oh yeah.
That's because all the electrons see those naked protons and they want to get back. And so they will jump back like that.
Ooh.
Now, there you go.
I touched the little, this part like right here. I was like, ooh. Okay. All right, so I'm doing work on our Wimshurst machine.
Yep.
And those electrons right here, I'm sorry, those electrons are not jumping.
Yeah, well,
They're jumping.
actually, when we had the screwdriver there, we had a conductor.
Yeah, oh, it was
Put it
able to
on
really
here,
travel here.
and so you got electrons on the bottom, excess protons on the top, and you gave them a path to get back together.
Yeah, and so what we have here, we know that we have a uniform electric field. What is this? I think a uniform electric field exists between the parallel plates, lines at the same distance apart, and so
Out of the positive in the negative. 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 That's the
Okay.
direction of the electric field.
yeah, and what happens is when we put our charge in here, it is attracted to the negative and repelled from the positive. Now, let's talk. We have that one equation with the electric field. The electric field is uniform; it's the same throughout. And this is one of our equations for electric field. This is the equation for the electric field.
Yeah.
Well, actually, no, it's not the only
That's
one.
the measured.
It's the measured, right?
The
With a
measured
test
electric
charge.
field. So you put your test charge in there.
Okay, so our test charge is always, well, in this case, we're going to say it's 1 coulomb. The positive charge, 1 coulomb, okay? We put it in here, it drops down. Now, I have to do work to put it up here.
Yeah, because that positive charge is attracted to the bottom and repelled from the top.
Yeah, and then if I let go, oops, this more is not as good as, what do you always do? You always go,
Well,
and
I have my other hand there ready to...
Yeah, and when I let it go, it falls. Now, the electric field is always the same. What do we know about the force throughout the field? So if I've got my charge here,
It's close to the negatives where it wants to be, and it's far from the positives where it doesn't want to be.
yeah, it has not as it's being attracted strongly to here and repelled not as much this way, right?
Oh, that's right, because it's farther away.
It's further away, right? And then as I bring it up here,
Now you got more repulsion.
okay, less attraction, and there's a give and take here, right?
Yeah.
And the force essentially is going to be the same throughout, okay? Because then sometimes it's going to have more attraction, less repulsion, more repulsion, less attraction. And essentially throughout the field, the force is the same. The charge is the same, therefore electric field.
That's what the idea of the uniform electric field, and that's symbolized by how close together the lines are. Remember, if you have a single charge, the field radiates out like spokes on a bicycle wheel in all directions.
All right, let's see. I think we covered everything that we needed
Yep.
to there. Okay. Since how much work depends on how much charge, a ratio of work to charge is most useful.
That's what we did yesterday. Remember that? We had the 1 coulomb, we had the 2 coulomb charge, and the force was different depending on the charge, but the ratio for each was the same.
Okay, so we said a ratio of work to charge is what did we say? Is useful. Okay, and we know that work is force times displacement.
And what does work do?
Okay, well, work will change the electrical potential energy,
That's right.
right? And we call this our electrical potential difference.
And
It's
that
gonna
you
change the
get that when
energy.
you divide it by the quantity of charge you're moving around.
Exactly. So essentially, the amount of work over the charge, or force consistent of a charge, or electrical potential energy over charge, it's all the same idea.
Yep.
Let me get our answer there for the electrical potential difference, which we know is a volt. Joules per coulomb, those are our units for that.
Yeah, the units of work over the units of charge, the units of energy over the units of charge, and that's a volt.
Yes. Okay. All right. So let's go do a practice problem. Okay. I'm going to just erase this part right here. I don't remember. Do we need this later? I can't remember. I think we'll leave it. Okay. We do.
Yeah, we
need
will lead it.
Okay. So you do 10 joules of work moving a 1 plus charge from the negative to the positive plate of the capacitor. Okay. So from here to here. From here to there, right?
So there's your 1 coulomb of charge, and you
Okay.
10 joules of work. What's the electrical potential difference?
So work was 10 joules.
Quantity of charge is positive 1 coulomb.
Okay, if I want to find the electrical potential difference.
That's just the work over the charge.
Yeah. Okay, so so 10 over 1 is 10 joules per coulomb, or 10 volts. Whichever
10
one you want to
volts.
write.
Simple, yes?
Yeah, this is simple enough. So it's gonna take, so it takes me 10 joules to move it up this way.
Yeah.
Okay, that 1 coulomb charge, and that describes. This is a property of the our electric field.
Yep,
Right.
inside a
It takes
capacitor.
10 volt. It will take 10 volts. Okay. Since
Remember this from yesterday?
review. Okay.
What are we going to get out of this?
Well, we are gonna get our ed, right?
That's right.
So we know that, let's see, this and this are the same thing. This right here, this is the same
So
thing.
instead of
right?
F over Q, you could put E times D.
So E times D, we get
Ed!
So there's a lot of different equations here. Okay, so we got Ed. Do you guys ever watch Ed, and Eddie? Strange show. Okay. All right, so that's Ed, uniform electric field. Okay.
And now-
we're gonna. Oh yeah. And now the electron pump versus the capacitor. Okay. So let's do it. So
We've got electron pump over here versus a capacitor, but this is noisy and dangerous.
So let's take a look at our.
So
Might should have took
this
this off.
is an electron pump.
Yeah, this is just like our machine up there, right? When we're turning the wheel.
Yep.
So this is an electron pump. We spin the wheel, we do our thing. And this is a capacitor. And there's a plus sign here. I'm gonna go ahead and add the pink to the plus and the silvery white
Now these are wires,
to the other side.
and wires have conductors on the inside of them. See that? There's a metal conductor on the inside of the wire, and it's surrounded by an insulator so that there's no short circuits, whatever the heck that means.
Okay, so first let's just go ahead and play. Oh,
I didn't see anything happening until you let go.
so no sparks over here, but check this out, right?
Okay, so this, an electron, what does an electron pump do?
What does a pump do? Well, a pump moves something. What is it? Boykin, how do you describe it? What's an air? What does an air pump
Tire
do?
pump, if you're
Tire
pumping,
pump.
pumping air in your tire of a bicycle,
Yeah.
it takes air from the atmosphere from one place and puts it inside the tire.
Yeah, so this is an electron pump, so it's going to take electrons from one place and put it to another.
So inside the capacitor here, and remember, it's just like the pie plate.
Just like it.
It's pulling electrons from one side and putting them on the other side, so we get a charged capacitor. So do that again. Pumping electrons, pumping electrons, pumping electrons, and then you, what the deuce is going on here?
It's like one of those like little like things, kind of, right? So once you let go, it still does its thing. What is happening? How is it still able to do its thing? Okay. Well, let's go ahead and do that thing where we do 2 pumps and 6 pumps, and then we.
I like that.
Okay, so I'm gonna just do 2 pumps. Okay.
1, 2.
Cool. Okay.
You turn too hard, you turn too fast, but that's okay.
Okay. Okay. And then I'm gonna do 6 pumps. Oh, that's going a lot longer.
It is going a lot longer. So if you pump twice, you're pumping a certain amount of electrons from one plate to the other. If you pump 6 times, you're pumping 3 times more electrons from one to the other. And so it keeps going.
Okay. So do you want to be able? Can you do the thing when I do it like this?
You know, I'm thinking we ought to wait on that.
Okay. You want to wait on it? That's
Yeah.
so cool. Okay.
Oh, well, all right, okay.
I like it. It was really cool.
So you go ahead and pump electrons.
Okay. So here we go. And then I should.
No, keep
keep
pumping.
going?
Keep pumping. Now let go.
It just stops
Now
dead.
put it down on the table.
Okay.
And what happens when you reconnect it?
Get this baby some juice. Whoa. Ha. It's alive.
What was that? It's alive! It's alive! It's dead.
Okay. So, what is going on here?
We're
got a
going to ask
capacitor.
you to
Oh, yeah.
see if you can figure out what's going on.
Okay, so keep in mind, we do not expect you guys to,
We want you to do the best you
do the
can.
best you can here.
Explain what we just saw when she was pumping the electrons by turning, and then when she let go.
Okay, so 3 to 4 sentences using these words. We have electron pump, electron flow, attraction, field, electron potential energy, capacitor work, repulsion force. So use these words and write 3 to 4 sentences explaining what happened there. Now just start from the beginning. Think about what's the first thing I did. What's happening when we pump electrons? What's going on there?
So do the best you can. Let's stop the video and see what you can do. Okay, so let's see if we can explain what's going on with the electron pump and the capacitor.
Okay, so I'm gonna go ahead and represent my electron pump by this little thing, and it's connected to the top and the bottom plate of
That's
the
what those wires were
capacitor.
doing.
Okay, so what was the very first thing that I did? We started pumping it.
You had to do work. You had to put
Yeah.
work in.
Okay, so I had to put work in to the pump as I turn the crank. And what happens? We're pumping electrons from here to here, right?
Yeah, so
Okay, so electrons are going to be going this way through the pump, and then they come back over here, okay, doing their thing, right?
simple.
Yeah. Now there's a certain extent to which and as we do this, we create that
Electric field.
Electric field. Excuse me.
And after, you can only pump so much because you get too much positive on the top and electrons won't leave. Say, I ain't leaving.
They're
You ain't
attracted
pulling
up
me
there,
away from
right?
this. And on the bottom, you got all these electrons. They're repelled, and so you can only pump so much before it just won't do it no more.
Yeah, it reaches that maximum threshold. And, and okay, so what happened next? So we were spinning, and then we let go.
When you let go,
Okay.
the handle kept spinning.
Actually, I'll leave the electron there. The handle kept spinning. What is happening there? Well, now the electrons are running back this way through the pump and going back this way, okay, through the pump. And what's happening now? Instead of us putting work in, work is being done
You're
on the
getting work
pump
out because the electrons are doing work as they go through.
as they go back through.
And how can they do work? Because there is electrical potential energy stored in the field.
Yes. Okay, that is making sense. Okay, so we talked about the electron pump, we talked about the flow. Ooh, we talked about attraction repulsion, right? When we're talking about why they can only store some.
Well,
I love when we do that. I love when it falls off the
class, are you okay, class?
Um,
Here, I've got this in this thing right here. It just came out. I'm just gonna hold it.
Hold it. Well, I think we're almost done. Maybe. Okay, and then we talked about the field, electric potential energy, capacitor work. We talked about it all. Okay. All right. So moving on here. And if you didn't get that, just rewatch it, and we're gonna.
We'll
talk
play
on
with it again.
more. Yes. Okay.
Yeah.
So what does each symbol represent here? We're talking about distance, electrical field, our test charge, force, work, and our electrical potential difference.
There you go.
Okay, let's do a practice problem here. So two charged parallel plates are 0.02 meters apart with an electric field inside of 25 Newton coulombs. What is the delta V between the plates? Okay, we've got Ed here, yes?
Looks like Ed to me.
Okay, so let's go ahead. So delta V equals, so Ed is 25 Newton coulombs and D is 0.02 meters. When I plug those in, 25 times 0.02 and I get 0.5.
0.5.
0.5 volts.
0.5 volts.
Okay.
All right, so you got 0.5 volts between the plates.
And then it says how much work will move the how much work will move the, that's the test charge, sorry. The +1 coulomb from the negative to the positive. So I'm doing work moving it over a displacement.
I think that's our definition of electrical potential difference, isn't it?
Yeah, it is.
Delta V is equal to
So work is equal to,
W over Q.
well, the delta V is equal to work over this, right?
Yep.
So we want to find the work. So that just means
Yep.
right? Okay, multiply this on both sides. Okay, so I'm gonna do the charge, which is a 1 coulomb charge, times the change in electrical potential, which is 0.5 volts. Okay.
I don't think you're going to need a calculator for this.
Yeah, that's just 0.5, right?
0.5.
0.5,
And a volt is a joule per coulomb. So you got joules per coulomb times coulombs gives you
joules per coulomb. That gives you a joule, which is work. Woohoo! Okay, so 0.5 joules for that. Okay. Now I had to think about what my equation was there for a second. That's okay.
Well, no, that's normal.
Yeah, it's normal. Okay. Okay, and that's the equation we just used. Woohoo! Okay, electrical potential difference. We could find any one of these things as long as we've got the other two. Okay. When it's not on there, it doesn't move it. Okay, you pump 0.8 coulombs of electrons from one plate to another in a capacitor. Okay, so my charge here is 0.8 coulombs.
Yep.
Okay. How much work did you do if the delta V, the change in electrical potential, is 8 volts? I'm just going to use the same equation, right?
Yep.
Right here. Okay, so work equals delta V, which is 8 volts, times my test charge, which is 0.8 coulombs. I was like, is that me? Mr. Boykin is so popular.
Yeah, I'm getting a call from Jurupa Valley, California.
8 times 0.8, and I get 6.4. Oh, I could have done that in my head. 6.4 joules. Okay.
Simple, yes?
Yeah, this seems simple enough.
And at this point in the school year, boys and girls, you should be pretty good at dealing with equations.
Yeah.
You got lots of practice.
Okay, so electrical potential difference in a parallel plate capacitor. We can use
Ed.
Yes, Ed. Okay. All right. Let's see. Are we gonna pause on this one? No, we're gonna do this one. Okay. All right. If the plates of a capacitor are 0.004 meters apart, so now our distance is 0.004 meters apart, and the
Electrical potential difference is 8 volts.
8 volts. Oh, same as before. Okay.
We're going to use Ed.
What is the intensity of the electric field? Yeah, it's just Ed. Okay, we're gonna use Ed. So
And we gotta,
let's see. We want the E, right?
Yep.
So I just divide by the D. Okay, so Ed equals the delta V over the D. My delta V is 8 volts. My D is 0.004 meters. Okay, it's gonna be something with a 2, right?
200?
8 divided by 0.002. Oh, we're both wrong. wait, no. Oh no, I did it wrong. 8 divided by 0.004. 2,000.
2,000.
Yeah.
Okay.
I was like, wait, that can't be right. 2,000 volts per meter. A volt is a joule per coulomb, right?
Yeah. And a joule, you know, it's newtons per coulomb.
Yeah, it is Newton per coulomb.
Yeah, and a joule is a Newton meter. So you
Oh,
got
yeah,
Newton
yeah.
meters per coulombs divided by meters.
Cancel. Coulombs are there. Okay.
Sweet.
Nice. Okay. All right, so we're gonna skip this one. I might save this one for later in class. If you want to go for it, go for it. Give it a try. How much time are we on there? Oh, it's hard to say, huh?
We got a
Sorry
lot.
again. All right, well, let's just call it a day. For your homework, what you're gonna do is you're gonna read page 492, and you're gonna do numbers 5 through 8.
Okay, that's page 492. There is a wonderful example problem. Read all of it. Make sure you understand what's going on as you do that. And then on the next page, 493, 5 and 6.
Whoop, whoop. Go get them.